Hello students, and welcome to this video of Study Unit 4 and detailing Karnaugh maps. So before we get to Karnaugh maps, we also look at this circuit. So we have this circuit and we have to find the resulting equation and then write that into a truth table. And then from that truth table we will obtain our Karnaugh map. We'll get to that a little bit later on. So here, I find it easier if you go from left to right and write out the output of each gate as you come across them. So from this side, you have the operation C and D in this gate, so it's C and D. It goes into this OR gate, so C and D OR B, and write down the output. And then they both go into this AND gate with A. So you have A and B or CD, which you write down the output, and this is the final output of this whole logic circuit. So the next step is writing down the truth table for it. Now you have your four variables A, B, C, and D, and you write down the 0, 1 values for them, as you can see, using the simple method. And then instead of, for me, it's easy, instead of going directly, you can, if you want to do like that, write out the output directly, but I find it harder because you have A and B or C and D. So what I do is I take it in steps, and my truth table mirrors my logic diagram. So here if we first start the C and D, so we get C and D, and we do the AND operation between these two columns, and you have C and D. 1, there's a 1, there's 1, and there's 1. And then the next step is the B or C and D. So we then have the B column and the C and D column. We perform an OR operation between them. So it will be, we're looking for ones. Aha, it's 1. So B or C and D, 0. There's a 1 and 0. That's 1. 1, 0, 1, 1, 1, 1. And then it'll only be basically be 0 when both columns are 0. So we're looking at B and then C, D, B and C, D. And so we have all these ones. And then the next gate, the next logical operation, is the final equation. So now I have to perform an AND operation between the column A and B or C and D. And then that will be our final output. So we, once again, for both these columns, if we have for between these two columns forming an AND operation, so we're looking for a 1. Well, both these have to be 1 for this to be positive. So both of them, there's a 0, 0, middle 0. Oh, there's a 1. Okay, but the other one is 0. So 0, 0, 0, 0, 0. Okay. Now we start with the 1s. 1, 2. Okay, so here we have both 1s. It's 1 and 1 and 1, 1, 1. So now we've transferred our logic diagram to a truth table. So this is our truth table output. So it's a lot easier, I think, in doing it like this instead of going directly from here to the output state. Now we come to Karnaugh maps. So Karnaugh maps is similar to a truth table because it presents all the possible values of input variables and the resulting output of each value. So it sounds a lot like truth tables, and it is, but they are organized slightly different. Where truth tables are in columns, Karnaugh maps are an array of cells in which each cell represents a binary value of the input variables. These cells are arranged in such a way to enable the simplification of a given expression simply by grouping the cells properly. So we want the simplification aspect of this, as already in Karnaugh maps. So here we have an example of a 3-variable Karnaugh map, A, B, and C, and this is how you would write it if you're doing a Karnaugh map. So you draw these blocks, this little line, and then on this side A and B, on the other side C, and you would number it 0, 0, 0, 1, 1, 1, and 1, 0. Now this is not your normal binary progression, although it is gray code. So just remember, it's not normal binary. We write it like this for a very special reason, and that is just so 1 bit changes at a time, and it just enables us to do the simplification. And on this side you have 0 and 1. So 0, 0, 0, 1, 1, 1, and 1, 0. And these blocks then represents A naught, B naught, C naught. Because it's a 0, it's a naught. So whenever there's a 1, which in this case is B, you will have B in its uncomplemented state. So let's say here, 1, 1, and 1, it's A, B, and C. Very important to understand this. So here we have A, and that's a 1, yes. B naught, which is a 0, and C, which is a 1. So wherever the we're looking at this block where it intersects, and we have on this side a 0 and a 1. So A is complemented and B is 1. So you write like A not B, and then C is a 0, so it's C not. Now we have a 4 variable Karnaugh map. We number it the exact same way as the 3 variable map in the gray code formula. 0, 0, 0, 1, 1, 1, and 1, 0. And then the mapping is exactly the same. Do you understand it? See, here we have 1 and 1 and 1, 1. So all these will be A, B, C, D. And here we have all zeros. So it'll be A naught, B naught, C naught, D naught. And here we have A, which is 1. B should be B naught. You have C, which is 1. And D, which is D naught. Exactly that. So as an example, we have this sum of products expression. And it's very important, you can only put in sum of products. You can only put in sum of products or product of sums, inversely, we're not doing that yet, into the Karnaugh map if it's in standard form, i.e. it must have all the variables A, B, and C. A, B, and C. So all these this equation must be in the standard form. Remember, we converted to standard form. This is why we did it, because we need a standard form. So you have A naught, B naught, C naught, and underneath we write, if it's a naught, it's a 0, 0, 0, a naught, 0, 0, and then if it's normal, just write a 1, well, non-inverted, so non-inverted, 1, 1, and not 0, A 1, B naught 0, C naught 0. And then we go and look at the array and see where this fits in. So here you have all zeros, so all these must be zeros. So you have 0, 0, 0, 0, oh, so that's a 1. The next one, A and B are both zeros, so we stay in this row. And for this column, C is 1. Moving on, you have 1, 1, 0, so A and B are both 1s, and C is 0. So we have 1, 1, and then C is 0, so there's a 1. And then the last term we have 1, 0, 0. So A is 1, B is 0, and C is 0. So that's how we map from our sum of products in standard form to a Karnaugh map. Don't worry about the open spaces, we leave them open. And now we come to the nitty gritty, why we do that. So we map the Karnaugh map as we do, so we can group them, and then use from that grouping, we can simplify it. So a group must contain 1, 2, 4, 8, or 16 cells, which are all powers of 2. In the case of 3 variable map of 23 equals 8 cells is the maximum group. So each cell in the group must be adjacent to one or more cells in that same group, but not all the cells in the group need to be adjacent to each other. So we only group cells where there is a 1. Always include the largest possible number of 1s in a group as prescribed by rule 1. So you can't have a group of 4 and 4 which you can group in a group of 8, and I'll show you the groupings just now. Each one on the map must be included in at least one group. The ones already in a group can be included in another group as long as the overlapping groups include a non-common one. I'll show you this. So we have 4 examples. Don't worry about the expressions. We don't, at this point, we don't care about it because it's already in the Karnaugh map. So here I have 1 and a 1 and a 1, 1. So we have to group them in pairs of 2, 4, 8, and 16. So here we have a 1. Can we group it with anything else? Are there any cells adjacent to it? No. And also you have to remember that these you can bend around. So the top and the bottom rows are adjacent. The left and the right rows, furthermost right rows, are adjacent. Now for 3 variable map, these doesn't matter, but these are still adjacent, and I'll show you in the other groupings. So in this one, there is nothing adjacent to it, so it's in its own group. So it's in its own group. But these we can group them 2, and then another group of 2, because we can't group them together because they're only 3. And we can group it like that, and then we can include a 1 of another group as long as they have non-common 1. So there is a non-common 1 not in that group, and also just to make sure we have a 1 that's not in that group. So here we have 3 groups. Now what do these groupings mean? These grouping means that we have now, for each group you will have 1 equation. So now where we have 1, 2, 3, 4 equations, we've now simplified it to 3 equations. Now in this group, remember the top and the bottom part are adjacent. So we can group these 2 with these 2 to make a group of 4, as shown here. And then we can group these 2 together and those together, because they contain a non-common 1. And this is exactly what we said, wraparound adjacency. Now moving on by a 4 variable one. So here we can group these 4 together and these 4 together. We group them together because they have non-common 1s. And unfortunately there's no group of 4 that we can group these 2 into. They have to be in their own group as is, because we can't group that with just that one, because that's a group of 3, which doesn't work. So in this case we had an 1, 2, 3, 4, 5, 6, 7, 8 equations, and this is now simplified to just 3 equations. Now in this Karnaugh map we can see we have 1, 2, 3, 4, 1, 2, 3, 4, and they are adjacent, so we can group them like so to have a group of 8. These we can group as a group of 4, because grouping these 4 with these 2 is a group of 6, which is not allowed, so it has to be a group of 4. And here is only a group of 2. So once again, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 equations have been reduced to, counting the groups, 1, 2, 3 groups. So that is why we do it. So determine the minimum sum of product expression from a Karnaugh map. Variables that occur both uncomplemented and complemented within the group are eliminated. These are called contradictory variables. So what do we mean by that? Okay, so we have this expression. We've taken it to our Karnaugh map and then grouped the Karnaugh map in these groups. So here we have 2 groups. So this means we're going to have 2 expressions from this. So we look at each group. Let's start with this group. So what we're telling is, if a variable changes in that group, moving from, let's say, from this one row to the other row, it falls away. And if it stays the same, in this case, we have a look at A is 0, and still inside the group, it's still 0. So it stays, but it's going to be complemented, because a 0 is a complement. So you write down A complement. A B inside this group goes from a 0 to a 1. So it goes from a complemented stage to an uncomplemented stage. So that means, according to our rules, it falls away. So B is not written here. And then to the other side, C, it just stays the same value, so it stays, and it is a 1. So that's the expression of this group. Now, looking at the bigger group, we have this. So A is a 0 in this row, and it's a 1, sorry, in this row. So it goes from uncomplemented stage to a complemented phase, so it falls away. So A is gone. B is 0 here and is 0 there. So it stays in its complemented form. And C goes from 0 to 1, so it falls away. So you see, if you have a bigger group, it is a lot easier for variables to be cancelled out. Yeah. So the aim is to get as big a group as possible, and of course it cancels out very nicely. So now we come to don't care conditions. Sometimes the situation arises in which some input variable combinations are not allowed. These conditions are called don't care conditions and are marked with an X or a D in the Karnaugh map. To illustrate this, we will look at two examples, BCD and a segment display. So it's remember the BCD, we show that decimal numbers from between 0 and 9 with 4-bit binary numbers. But 4-bit binary numbers, you can show a number bigger than 0 to 9. So there are BCD or binary conditions in the truth table that is not valid for BCD code. So invalid conditions occurred when the binary goes over 9. Decimal binary, this, as shared in the following table. So this is our truth table for BCD code. Specifically, we are mapping towards a specific output Y, and this is just the random output we chose, which is high when the decimal number 7, 8, and 9. So it's 0, 0, 0, and then at 7, 8, and 9, it is high. But this value, 10, here, is not contained in our BCD code. So it becomes an X. So don't care. We don't care what it is. It's very important to note that when you're writing out your truth table, you have to use the truth table as a complete truth table. So you have to include the rows, even though when you write down, it stops here. It can't be anything else in the BCD code. We still have to finish our truth table. Remember, when we're filling out the truth tables, here we have 8 zeros, then we have to have 8 ones to complete the truth table. But just for these values, it's don't care values. But for a don't care condition, we have to also map it to the Karnaugh map. So these ones we map, and there we have them. And we also map the don't care conditions in the Karnaugh map with X's. But now the thing is, with don't care conditions, we can group them with ones. So if we didn't add the don't care conditions, we will have two pretty small groups, that group there and that group there. And then without the don't cares, this will be the equation. But because we can group this one with these ones, we can group with these other 6 don't cares to make a big group of 8, and also we can group this one solitary one with another don't care for a group of 2, which we can then simplify to this. Now if you draw the logic gates, I actually would like you to draw this, draw it and then see for the BCD conditions if this is correct, if this gives you the same output as this in terms of these conditions. We don't care about the don't cares, it doesn't matter, we're never going to get to them. But draw the logic gates and then see if without the don't cares, if it's the same as with the don't cares. Now this is a lot simpler than this. Now also in your assignments you have a 7-segment display, which we've talked about, and here we are, instead of looking at the A variable, the A segment, we're looking at the E segment. Now 7-segment display is just all these segments are LEDs, and if we want to light up one of those LEDs, we just send a 1 to it. So enabled to, so now we're looking at the E segment. And this is how the 7th segment displays numbers from 0 to 9. So, sorry, the C segment. I chose it because it's the segment that's least common. So here we write down our truth table, A, B, C, and D, of all the 4 BCD inputs. And here you can see at number 10, it is don't cares, because BCD code goes only up until 9. But here we had a look at C is active there, it's not active, it's there, not active, not active, not active, active, not active, active, not active. So in 4 cases it's active, and we just write in which cases we see which time it's, so it's at 0, this segment is lit up, this segment is not lit up in 1, and 2 it's lit up, 3 is not, 4 is not, 5 not, 6 it is, 7 is not, 8 it is, and 9 is not. So whenever it's lit up we give it a 1 at the, so this is at 0, at 2, at 6, and at 8. And then don't get conditions for the rest of them. So I've just simplified it a little bit. This is the equation from the truth table. So whenever there's a 1, you write down the equation. So there's a 1, and this is a 0, 0, 0, so it's A naught, B naught, C naught, D naught. And then, or, the next condition, A naught, B naught, C, and D naught, which is that. And for the next one we have A naught, B, C, and D naught, which is that. And now we have A, B naught, C naught, D naught, which is also 1. For the rest of them, for all the zeros, we don't write them down. So this is the equation we have, and from there we go to our Karnaugh map. We fill it in where we have, and then we group them. So because the adjacency, we can group these two together, and we can group these together. Now we can also group that one with that one, but then we've a 1 dangling around, which is, yeah. So we can group all, the idea is to group all the ones in as few amount of circles as possible. So few, the least number of groups. So we have 2 groups. So A goes from complemented to uncomplemented, so it falls away. B is complemented, so it's B complement, and C and D stays in its complement form, so it's B complement, C complement, D complement, and then or A stays in its complemented form. B goes from complemented to uncomplemented, so it falls away, and then C is in its, here we go in that row, in its uncomplemented form, and in its complemented form for D, which is A naught, C, and then D naught. And then that is the simplified form of the equations. And then from there you can draw the logic diagram and the gates to realize that the lighting up of that circuit. So that is Karnaugh maps. The videos seem to be getting longer and longer, but the content is getting a lot more difficult than it was a couple of chapters ago. So sorry for the long video, but I hope this helps you a lot. Good luck.